oh, and also just for your information, the one that I showed you was the reverse fault example, but we have a similar one in 2D, the stripe-slip fault example. So if you get motivated, you could try running that on your own. Okay. So in 3D Hex 8, this is actually probably our most comprehensive set of examples, and so hopefully people will spend some time going through these. But for each of these examples, we use the same extremely simple mesh, so I don't know if I'll actually go through the process of creating this mesh. It's a hexahedral mesh, so it's the whole thing is just a brick composed of hexahedral cells. And so we have 21 examples in here, starting from the very simplest at step 01, and then they get progressively more complicated. This final one that I'm going to be talking about today, step 21.config, is the greens function example. So I'll just look, we'll look at the files. We can look at the basic files that go into it. Where's my oops. Let me make that bigger. So this is the pilot app.config file that's used for all of the examples in 3D Hex 8. They all have similar things. This is just verbosity stuff, which is what things we're going to show progress related to. Our mesh generator, where it's mesh.io qubit again. This is the mesh that we use for all of these problems. It's a Hex 8 mesh. For all of the problems, we have two materials. We have the upper crust and the lower crust. And then by default, we're just using elastic properties for both the upper and lower crust. In some of the examples, we'll use things like viscoelastic or elastoplastic, things like that. But for the problem we're doing today, everything is going to be elastic. And then finally, we just have our PET-C solver options at the end.
This is the same pilot app file we went over in session 1.
Okay, right. So this is all just review. So now, the one thing that's new for today my machine is backing up now, so it's slow. Really slow. Might put some of the other stuff up there. Okay. So this is the part that's specific to greens functions. So as before, now you'll notice that all of these things have greens functions as the problem type. And when we change the problem type to greens functions, Pilot will automatically look for files with this name, greensfunctions.config. So the first thing we do, we give it our fault ID, which we've set as 10. And again, this is the same as for the 2D. For our fault, we change our interface type to fault cohesive impulses, which just means that it loops over all of the vertices and computes the response for each impulsive step. Now in this case, because we're doing a 3D problem, we can do both types of slip. We can do both left lateral and reverse slip. So here we're telling it we want to do left lateral, which is 0, and reverse slip, which is 1. And then finally, we have to tell it where to get the slip impulse information. And that's contained within this impulse amplitude spatial dB file, which we can look at that real quickly. So what we do in this file, all we do is tell it the amount of slip, and this will apply for both our left lateral and our reverse slip components. So we're going to specify it at 35 different locations, which is every vertex on the fault. And so that means our data dimension is 2, since we're specifying the impulses over a plane. Our spatial dimension for the problem is still 3. And we're giving our coordinates in kilometers. So what we're doing, this is your x, y, z coordinates. And we're telling it, instead of, this means that if we're computing a left lateral impulse, the slip amplitude is actually -1. So that means it's actually a right lateral impulse. It also means that when we generate an up-dip impulse, we switch the sign so that it's now a down-dip impulse. So we have that. And then you'll also notice that we have a set of vertices where we're not giving it any slip at all. So what this allows us to do, one of the things with Pilot is you typically don't want to specify slip along the edge of a fault. So this allows us to exclude vertices from being included in our greens functions so that it won't generate any slip for the vertices where we give it a 0 in this file. So that was our greensfunctions.config file. The final one is our step21.config file, which is specific to this problem. Really slow. Actually, let me put some applications. Okay. Okay, so in this one we do the things that are specific to this one example. So you'll notice that one thing that I changed in this file in relation to some of the other examples here, rather than saying time dependent here, I said formulation, which is more general than saying time dependent, because formulation can include any type of formulation. And in this one, it's a, problem. Yeah, not pilot app.time dependent. It's pilot app.problem rather than pilot app.time dependent. That means it can be specific, it can apply to either a greens functions problem or a time dependent problem. So again, we do things like give it a total time of 0, time step size of 1 year, and we're again doing, let's see, okay, yes, very simple boundary conditions. So we're applying boundary conditions on the positive and negative x faces and then on the bottom of the mesh. So we have an array of one fault, which we're calling fault. And again, we're outputting over the domain. In this case, we're not bothering to output the solution over the ground surface. We're only going to output at the points that we tell it to. And so we're going to set the points output to output solution points right here. So then for our x positive boundary condition, we're going to constrain both the x and y degrees of freedom, giving them zero displacements. We're going to do the same thing for the x negative face. And then on the bottom of the mesh, we're going to constrain it in the z direction. So for our fault, we have an ID of 10. We're giving it the label of fault. These are hexahedral cells, so that means that the fault is composed of quadrilateral cells. So that's Fiat-Lagrange cell type. And again, it has a cell dimension of 2 since it's 1 dimension less than our problem dimension. And then finally, these are the actual file names that we'll create. For the domain, everything is going to be in step 21.h5. For our points output, we'll have step 21, points.hdf or .h5. And the file that we're getting the points from is this greensfunctions points.txt. And then we have to give it the spatial dimension of the points as well as the units that we're using to define the points. Then finally, we get to our fault output, HDF5 submesh. That's for our fault output, and that's going to give us the area of associated with each impulse. So that means when you apply an impulse at a vertex, it's not just zero area, because there's when you do the integration, the area is actually a portion of each fault cell that's attached to that vertex. And then so it'll be a linear function. And then we're also going to output the impulse amplitude that we apply. And we're not really going to do anything with our state variable output. And then this is, well, okay, that's for debugging. You can also output partition information when you run this problem in parallel. So the this file here, that's where we're going to compute the solution at points. And we're just going to compute it we've computed it at several different z values, I guess. So to run this, we follow the directions in greensfunctions.config. And I'm going to kill some of my things that are, so we don't need this. Oh, don't need that. Okay, so again, it looks like it's time stepping because it's computing the solution for a bunch of different fault vertices. Okay. So now, get rid of the 2D stuff. So we'll look at what we've done. So we can look at all of this. We'll turn some of it off to start with. We'll turn the entire domain off. And so if we look at that. So this is our fault. Let's see. Yeah. We'll turn that off. So this will be our actually our right lateral component of slip that we're applying. We'll look at what that does in terms of our, we'll do the total displacement, and we'll make those points big enough to see.
Charles, why not use
and then
those are displacement vectors?
Oh, okay. All right, I can do that. So what I'll do, I'll scale those up a little bit.
It was up near the top with the edit.
Up near here?
Down a little further.
Yeah. Down there? No.
It's in the middle.
It's in the middle. Okay, they've changed. Oh, there it is. Okay. I don't really like the new way that Fairview works. I think that's enough. So this shows us what it's doing. So what I'm showing, this is the right lateral component of slip. So what you'll see is that it only shows up in every other one. That's because we're alternating between the right lateral component and the down dip slip component. So if we wanted to see just if anything's going on at all, we'll just look at the slip magnitude now. And so then you can see, so that this first one was what you got from the right lateral slip. It makes sense. You're getting displacement in this direction. And then up dip, you're getting vertical components of displacement here. And so then you just continue going through the different vertices on the fault, and you can see what the response is at all of these points. Okay, they're getting pretty small now. There we go. And what you'll notice is that we've excluded, go all the way through, you'll notice that we didn't apply any slip along the edges here, here, or here. And that's because in our impulse amplitude spatial database, we gave those all values of 0, so it doesn't bother to apply any slip along those vertices. The other thing that we can see here, so let's see. So this would be the area associated Just get me. All right, let's see. So does the area then compute? Okay, so it just shows what the area. So for each vertex, it'll have a certain amount of area associated with it. So it's, I guess, yeah. So these are. It's going to be 0 along here. Oh yes, it's going to be a minimum along the edges. Yeah, minimum along the edges because they're attached to fewer cells. So here, the maximum are these vertices here, which are attached to 4 cells. So the area field is one that you could compute, or that you would make use of if you want to compute, say, the seismic potency, or it could be used in computing the moment, but if you're doing the moment, you have to have a lot more information about the material property variations. So there's that, and then this just shows the impulse amplitude field. So here you can see impulse amplitudes -1 for all of the cells in here, and then there's 0 along the edges. The only other thing I can think of is just showing we can move that up. Just what the response is for the entire domain. So you can just see what happens there for all of the different fault slips that we apply. So that is step 21, and as I said, it's all we're doing is computing the Green's functions. But to do an inversion, you would do something analogous to what we did for the 2D example.
So the question is -1 because Z is positive down dip. And the impulse amplitude is related to whether we go right lateral or reverse or normal slip. For a vertical fault, we can't really distinguish between reverse and normal slip. So it depends on which direction our fault normal ended up, for whether our, which side goes up and which side goes down. But the reason why we were thinking in terms of right lateral slip, so that's why we set it to -1, whereas +1 is left lateral slip.
Yeah. In reality, it's not very often you would have a vertical fault with dip slip motion on it. Okay.
Are there other questions?
I don't know if people have been able to follow along much as we're doing it or not.